data we're trying to collect from the cosmic dust are angle of entry, electrical charge, velocity, and atomic composition. At the top of the bucket are 4 metal grids. The first and last are connected to electrical ground, and the middle 2 are connected to each other and then to a signal amplifier. The outer 2 grids, along with the casing of the bucket, form a Faraday cage around the 2 middle grids. A Faraday cage is a metal enclosure that greatly attenuates electrical fields originating from the outside. As cosmic dust travels through space, they eventually become electrically charged due to interaction with cosmic rays and plasma. The CDA takes advantage of this fact because the rate at which these charges accumulate depends on the environment. So once our charged dust passes the first grid, it will be inside the Faraday cage, and its electrical field will start to get picked up by the second grid. This will cause the voltage on the 2 middle grids to rise since they are electrically connected. As the charged dust passes the second grid and heads towards the third, the voltage on the second will start to drop, while the voltage on the third will start to rise. Since they are electrically connected, the combined effect would be that the voltage will be about the same for that time period. Once the dust passes the third grid and heads towards the fourth, the voltage will start to drop, hitting 0 when the charge goes through the fourth and final grid. Now it's outside the Faraday cage, but still inside the detector. The journey of this dust particle is far from over, but let's step back and look at what data we've collected so far. The shape of the electrical pulse signal that the dust has created can tell us a few things. First and foremost is the charge of the dust. That's directly related to the voltage created on the 2 inner grids, which also corresponds to the height of the waveform. The width of the waveform corresponds to the time the dust spent between the first and the fourth grid. Since the distance between these grids is known, the speed of the dust can be determined. You'll notice that the 2 inner grids are at an angle relative to the outer 2. What this does is it changes the distance between the first and second grid, and also the third and fourth grid, as you move from the center of the bucket towards the wall. So, at any given speed, the dust particle will spend different amounts of time between the first and second, or third and fourth grid, depending on how far it is from the center of the bucket. This time corresponds to how steep the left and right slopes of the pulse are. Knowing how far from the center a dust particle enters and how far from the center it exited allows us to calculate its angle of entry into the bucket. This is good. It's really good. As the dust particle leaves the Faraday cage, we know its charge, speed, and direction. This is 3 out of the 4 pieces of information we're looking for. All it took was 4 grids and clever geometry. After leaving the Faraday cage, the dust particle continues through the bucket until it slams into one of 2 sensors that line the bottom of the bucket at up to 20 kilometers per second. At this point, the dust disintegrates into smaller charged and uncharged fragments, plasma, neutral atoms, ions, and electrons. The bigger of the 2 sensors is the ionization impact target, or IIT, which is a gold-plated ring. Since the IIT is electrically grounded, when a dust particle disintegrates onto it, some of the electrons created in the impact will be drained in the ground connection, while the ions will be accelerated towards an ion collector, which is negatively charged and located above the IIT. Some of the electrons will find their way to the ion collector if they're fast enough and headed in the right direction, despite being negatively charged. Based on the charge collected at impact time on the IIT and the ion collector, we can estimate the mass of the dust. In the middle of the IIT ring is a grid that's electrically grounded. 3 millimeters below that is the second sensor, the chemical analyzer target, or CAT. Cat is plated with rhodium, which responds differently than gold to dust impact. After an impact, electrons will be drained by the grid. Ions will be attracted by the ion collector. Since the attractive force is constant, the acceleration on the particle will be based on its mass, A equals F divided by m. This in turn determines how quickly the ion gets to the ion collector. So, the heavier the ion, the longer it takes. This arrangement forms what is known as a time-of-flight mass spectrometer. By comparing the arrival of the ions on the ion collector, we can determine its mass-to-charge ratio, which is based on its atomic composition, the final piece of data we've set out to measure from the dust.